Our fourth and final method for completing quadratics is completing the square. Please keep in mind that you're really mainly going to use method 1 and 2, which is factor or use the square root method. And believe it or not, the one that kids forget the most is the square root method, which is the easiest. So important things to remember about completing the square. A completed square is a quadratic expression that factors in the pattern a squared plus 2ab plus b squared, or minus 2ab, and then again this would be positive, and the factors come out to either be double positive or double negative. So an example of that for you to look at would be if I had x squared minus 10x and then plus 25, notice that this number is a perfect square, right? And it's a perfect square of 5 times 5. So the factorization of this will come out to x minus 5, because the middle term is negative, and then x minus 5 again, right, because that's the identical twin term, making it a completed square. Negative 5 times negative 5 is 25, but when I add these two terms together, I get negative 10. And interestingly enough, completing the square is the universal method to solve quadratics. It will solve any of them, but you don't want to do the most difficult process to solve the easiest problem. Again, we're going to focus mainly on assessments on method 1 and 2, with a few of quadratic formula and completing the square on an assessment. In fact, the mathematical proof for the quadratic formula is made using completing the square. There are plenty of videos on YouTube if you want to look at them to see how that works. It's not something you'll be assessed on at any time. That's just interesting for those kids who want to see it. Completing the square can also be used to rewrite a quadratic function from standard form into vertex form, meaning you can take an equation that's in this form and rewrite it using the form from Unit 2 for transformation of functions. So that's another very important use for it, which is used a lot in upper level math. So let's take a look at how to actually just complete the square. So let's say I had this problem, and I wanted to figure out a c value that would give me an identical twin number that would add the 2. And I tried to make it easy there. That would make c equal to 1. And 1 is the perfect square that students forget a lot. So if that were the case, I would have x squared plus 2x plus 1. And that would factor into x plus 1, and then x plus 1 again. 1 times 1 would be 1, and 1 plus 1 would be 2. So let's see if we think about this one, right? So I need to think of a number that's going to add up, that's an identical twin of 8. Sorry, that will add up to 8 as an identical twin. That would be 4. But if I square it, because it has to be squared, it would be 16. And the reason it has to be squared is because we're talking about a quadratic. And so if I rewrite that expression using that, I have x squared minus 8x plus 16. And that would factor into x, be careful here, minus 4, because the middle term is negative, and then x minus 4. Those are your identical twin factors. Now, very useful later, since we looked at the first two, would be to actually rewrite this as x minus 4 squared, because there are two of them, and this one would be x plus 1 squared, and that's actually where it gets its name. I want to show you two examples first. So let's think of this one. What numbers would have to be identical twins to add up to negative 18? That would be negative 9 and negative 9, but when I multiply this together or square them, I would get 81. And so the expression would turn out to be x squared minus 18x plus 81, okay? But then the factorization would be x minus 9, x minus 9. Again, why are they negative and the first one was positive? Because of the middle term. That one's positive. These two are both negative. So my expressions will be negative, and this would be x minus 9 squared. So then we get to one that's a little bit harder. And so that's when we start to come up with, well, how did we actually do these? The way we did these is we took half of this number, right? And then we multiplied it times itself, otherwise known as squaring it. And so when you get to a one like this, it's like, what number do we add together plus an identical twin to get 5? We really need this little mnemonic key device here, which is to do half of b, so b over 2, and square it, and that will always make a completed square. Half of 2 is 1, 1 squared is 1, half of negative 8 is negative 4, squared is 16, half of negative 18 squared is 81, half of 5 is 5 halves squared, which would actually come out to 25 fourths. And I know that may look a little scary at first, but it's just a number we need to write down because we know what the factorization is going to be. The factorization is always half of b. So even though we write this down and we're like, wow, that's a pretty intimidating looking expression, right? This expression right here is pretty intimidating. We don't have to really worry about what c is because we know that the factorization is always going to be half of b, so 5 halves. And you do not want to do this with decimals. You'll see more why when we solve problems. And so this expression would come out to x plus 5 halves squared. So now that we've seen how to make a perfect square, let's go over the steps of how to actually use it to solve something. And this is where we'd really want to take some notes. So step-by-step instructions for solving a completed square to solve an equation. First thing you're going to do is rewrite the equation into ax squared plus bx equals c. You actually want the constant over here, not 0. Though if you set it equal to 0, you can just move it over. You're always going to factor out an a if a does not equal 1. That is extremely important, and you'll see an example of that in just a minute. If you don't, the equation won't be balanced, and obviously if an equation is not balanced, it can't be correct. The next thing you're going to do is calculate b over 2 squared. That was the whole purpose of this. If you wonder what was the purpose of this, is to help you understand why we need b over 2 squared. And then add it to both sides to balance the equation. You're going to rewrite the problem as a perfect square using b over 2 to factor the left side. That's what we did here. So that's this step. Okay. Then you're going to use method 1, the square root method, to solve for x. Because if they're all squared, we can get rid of that in an equation by square rooting. And that's the process. So I would write down these steps, rewrite this, factor, calculate. I'll give you a second to do that, and we'll look at some examples. All right, so these examples are the same ones we solved just a couple of minutes ago with the quadratic formula. I like to show them to you you get the same answer, and also to show you that maybe completing the square is an easier way in some instances. So in this problem, again, it doesn't factor 1 times 4. If we have 1 times 4 and we have 2 times 2, there's no way we can get 2 by subtracting them. That's how you think about factoring. So we are going to use the completing the square method. Completing the square method using step 1 is to actually use that number on this side because we need to solve an equation. And I actually put a little blank there because we're going to hold the place value for what the completed square is. And you'll notice what I did there. This side of the equation right here is exactly the same, right, as this example we did here. I mean, it's the same problem as this. That blank is the c. All right, so the same number we used here, we used 1, we're going to put right there. So we put a 1 here because 2, right, we're going to do b over 2 squared, right? So in this case, it would be 2 over 2 squared would be 1. So we'll put a 1 there, and then we'll add 1 over there to balance the equation. So here we'll have x plus 2, x plus 1 is equal to 5. This is a perfect factorization of x plus 1 equals 5. This will then factor into x plus 1 squared, and that equals 5. And now we're going to solve it using the square root method, which would be to square root both sides. Don't forget your plus or minus over here. So as soon as you put a square root in a solving problem, it has a plus or minus. So these will cancel. They actually inverse. So x plus 1 is equal to plus or minus the square root of 5. And then using reverse Gelmdas, we will subtract 1 on both sides, and you'll get the exact same answer as you did with the quadratic equation. You get -1 plus or minus the square root of 5. So let's go back and look at that example. So taking a look at the second example here, notice that it's not already set up for 0. It's just like the one we did earlier when we did the quadratic equation. So we're going to want to start by setting it equal to 0, zeroing out, as some people will say. Just make sure, again, that you're careful with your like terms. All right, so add this over here. And, one of the most important things you do, because when you do this process right here, again, it's really important to make sure that this lead coefficient is positive. So when you zero this out and you set this equal to 0, if you have a lead coefficient that is negative, that's a bad thing, just in general for quadratics throughout the whole chapter. Make sure you combine your like terms, as we mentioned on the previous example, and make sure that you haven't made a boo-boo at the beginning. All right, so now what we're going to do is we're now going to, doing this process, you would say, okay, well, it doesn't factor, I want to complete the square. You would actually move the 40 back over here, and just make sure when you do that, that you make sure that it is negative, right? It's a negative 40. When you get a little better, you might just leave this term here, right, and then move forward with it. But, on a test or something, I will probably label the problem that requires you to complete the square, so you'll know that. So, but if you were doing a test or an SAT or something, you would not know that necessarily. Okay, so I'm going to leave my little blank here like we do. And that blank is to be completed, but we need to make sure we abide by rule number 2, or step number 2, which is to factor out an a if a is not equal to 1. So in this example, a was 1, but over here, a is 2. So before we do anything, we have to take the 2 out using GCF factoring. Okay, and then that is where we're actually going to complete the square. And notice I just kept an example that we had earlier. Half of 8 is 4, negative 8 would be negative 4, square would be 16. But see that whole process, you're going to take half of b, which is negative 8, and you're going to square it. So that would be negative 4 squared, and when you square something, it's always positive. That's an important thing to remember about math, about algebra 2, is that squaring something makes a positive number. So you're going to add 16 here, but you have to be very careful about what you're actually adding here. You're not actually adding 16 here, right? Because this is being distributed. So that's not really 16, it's really 32. So you can either say 2 times 16 if you want, or you can just say 32, however your brain wants to deal with that. Okay, so to balance this out, this is negative 40 plus 32. That's going to come out to negative 8. So to balance the equation out, I have negative 8 is equal to 2. I'm going to go ahead and factor that. So that would be x minus 4, identical twin factor of x minus 4. And when you get better at completing the square, you're of course just going to want to write that as negative 4 squared, which is the process we need. So once we get to here, the question is, well, what do we do? Well, we're going to, if you look back at the steps, these steps are super helpful to have and understand, is we're now going to use method 1, the square root method, to solve for x. So I'm going to reverse Gelmdas. There is nothing to add or subtract over here, but there is something to divide. So we're going to start by dividing. Please don't ever distribute this. It does not have the same base or the same exponent, so it cannot be distributed. So over here we get negative 4. That, of course, cancels out. So we've completed the addition and subtraction, and then now the multiplication step. We're now going to square root. Don't forget that when I square root this, we have a plus or minus on it. So that's going to come out to, don't forget the square root of a negative is an I. This will come out to plus or minus 2i. And that's going to equal x minus 4. And then to finish it up, we are going to add 4 to both sides. And we'll get the same answer that we got earlier. Let's take a look at what that looks like. So we end up getting 4. Remember, the real part comes first, and then plus or minus 2i, the imaginary part. And that is equal to x. So if I go back and look at the, here at the same problem under the quadratic formula, I got the same answer, 4 plus or minus 2i. And here I got 4 plus or minus 2i. So you may say, why did we learn this process if we already have the quadratic formula? Some students like this process because it's very algebraic and it follows the steps of reverse Gelmdas, while using the quadratic formula is sort of, it's vague, and we'll never use a formula like that again in Algebra 2. So I need to teach you the quadratic formula so that you're able to, be able to do physics and other science subjects, but completing the square is the algebraic process, and that's an important thing to understand about it. So the other thing that completing the square can do is it can actually rewrite functions into, from standard form, ax squared plus bx plus c, into vertex form, which is really neat to connect this unit to the transformations unit. So the way that that works is you're still going to do the same thing, but instead of setting it equal to 0, you're going to set it equal to f of x or y equals. You're still going to want to have a space here. And remember, the reason it's doesn't factor is there's no way to turn a 1 into a 6. So you want to remove this from the problem and put it over here so that the problem has room to complete the square. So we're now going to have f of x minus 1 is equal to x squared plus 6x plus that space that you've seen in the previous examples. And that space is going to be filled the exact same way. We're going to do b over 2, so 6 over 2 squared. And so that would be 3 squared, which would be 9. So we're going to put 9 here. We're also going to add 9 over here to balance the equation, so the algebraic property of equality. So we're now going to rewrite this as f of x plus 8 is equal to, we can go ahead and factor that if you want, and you might have realized that this factorization step is always going to be the middle term squared. I'll do it one more time, and on the next example I'll show you that you can kind of skip this step. So x squared plus 6x plus 9 will factor into x plus 3 twice. And so the final thing is to have f of x plus 8 is equal to x plus 3 squared. And you may say, well, how is that the same as the transformation unit? And believe it or not, in different places in the world, this is considered vertex form. But the way that we learn it, especially under Virginia State SOLs, and you might learn this eventually when you take pre-calculus, that this is a quadratic, and in that format, it's over there. So even in the United States, in pre-calculus, that format is a little bit more regular. But we know it like this: f of x is equal to x plus 3 squared minus 8. And if you remember from the unit on transformations, the vertex of this problem would be, remember, h is always opposite, so -3, -8, and you would graph your quadratic just to sketch that. You know, -3, -8 is right about here. You would do 1, 1, 1, -1, 1, 2, 4, -2, 4, and then you would graph your quadratic. And we can easily access that on Desmos, which is what's cool. So let me show you the Desmos, and I will type it in. So we'll type in, you got to use y equals or f of x equals. I like to just use y equals because it's easier. And then x minus 3 caret squared. I hit the right arrow key, minus 8. And you can see, I'll refocus that. Look at that, right? Oops, I made a typo. I put a minus there. So exactly like we did our sketch here, right? So it's pretty neat that and it's not even, if I were to be honest with you about why vertex formula is so useful, it's extremely useful for problems like that. And that is something you'll have to do in pre-calc and calc later. Now let's take a look at this one. So same situation, this problem doesn't factor because of this, but even if it did factor, to put it in vertex form, I still would want to move this over, because remember, factoring is important for solving, but we're not solving this problem. We're trying to write it in vertex form. So you can use completing the square to get something out of vertex, put something in the vertex form, regardless of if it factors or not. All right, we're still going to use our little blank here, so plus a blank. Okay, but we have to factor that 4 out. That's the most critical rule to remember about all of Algebra 2, is that when you have a coefficient, you have to GCF. And that's consistent with when we learn transformations. So just keep that in mind. It's very consistent. Over here, this would just drop down. In fact, I'll just hold off for when we complete the square. So here we're going to complete the square by taking half of b squared. Nice little easy number. 2 divided by 2 squared would be 1 squared. And so the completed square here will be 1. However, the 1 here is not really a 1, because it's really 4 times 1. So you can either write 4 times 1 or just say it's 4, however you want to do it. So in the next step, we now have f of x plus 7. And then over here, we're going to have a 4 leading coefficient. That's really important. You know, thinking about unit 2, which is what we're replicating here, that is the vertical stretch, meaning that's going to make all of my output values 4 times larger. It's going to make a very narrow parabola. So this step right here where you factor this into x plus 1 and x plus 1, once you get better, you can actually skip this step and just write x plus 1 squared. There's nothing wrong with doing that, and if you already understand that, please feel free to do it. And then here, we're going to need to move the 7 over. Again, in pre-calc, this may actually be standard form, so just keep in mind it's not as weird as it seems initially to us. But we're going to want to move that over so we have it in our H and K format that we're used to seeing. Okay, so here we go. And so this one would have a vertex at, right, don't forget H is always negative, so -1, -7. It's going to be very, very narrow because what happens is, you know, if our vertex is here, instead of doing 1, 1, it's going to be 1, 4, -1, 4. Instead of doing 2, 4, it's 2, 16. It's like way up here. So let's take a quick look at Desmos for that one now. So if I were to type that one in Desmos, I would have y equals 4x plus 1 squared, right key over, oops, didn't square that one, right key over, and then -7. I like to just double check. I did make a typo just a second ago, so yep, it looks good. So notice it's way down here, and notice it even shows you, right, over 1, up 4 to get to that y-intercept. So very neat and nice way to check it on Desmos. In fact, if you wanted to, you could even type in the original problem to just correlate that you have the right thing. So that was y equals 4x squared. I'm just going to skip over here and look at it. Plus 8x minus 3. And you can see that it graphed over top of it. So that's that one. That's that one. Red is my answer. Blue is the question. I know I have it right.